Hey there guys! So today we're going to talk about thermochemistry, and this is a little bit different this time. We've got a note packet that we're actually going to follow along with throughout this unit and do some practice problems with it as well. So let's go ahead and dive right in. So if you'll see on your packet, we have some terms that we have to start with. So this unit is thermochemistry. Let's kind of like figure out big picture what we're going to be talking about. So thermal is usually when we have heat, and heat is a form of energy. And so if we have thermochemistry, we're actually having these reactions that can transfer energy in the form of heat, if you want to be more specific, to or from surroundings. And so that's what we're going to be talking about a lot in this unit. And so let's first define energy in terms of chemistry and then go from there. So energy is the ability to do work or produce heat. All right, and so we're going to be calculating a lot of different forms of energy throughout this unit. And so if you see here, it says sum of potential and kinetic energies in a system. So we've got to understand from a chemistry standpoint, what are the potential energies, what are the kinetic energies? And so that's going to take us down to this graph. So if you see here, it says the potential energy is the energy of position. We all know that. Maybe you've had a little bit of physics in your background and things like that. When we talk about potential energy in the form of chemistry, we're talking about the energy that's stored in bonds. So we're looking at that potential energy, the energy that is stored in bonds. When we talk about kinetic energy, on the other hand, we're talking about these little molecules actually moving around. And I'll give you a better example of what that means in just a second in a simulation. So we're looking at the sum of those potential energies, so the energy stored in bonds, and the kinetic energy, the actual movement of those molecules. And that is going to be the energy that we are putting together to get our total energy of the system here. And so what I have to talk to you about first, there's a little simulation. And so we want to talk about the potential energy of these atoms. And so remember that potential energy is stored in bonds. Well, what I have here is a little graph that is showing two neon atoms that are a certain distance apart. And so what I can do is actually move these little neon atoms closer or further apart from each other. So let's notice what is happening to this graph as I'm moving these molecules or these atoms closer or farther apart from each other. Right now, where we are sitting at this distance from each other, so this is the bright spot that you see here is the nucleus of this neon atom. I think we're dealing with neon here, yeah. And this bright spot is the nucleus of this neon atom. Well, right now they're a pretty long distance away from each other, but as they're getting closer and closer together, we see something pretty cool happening. So it's actually going through a simulation now. You see how they're getting closer, and what's happening to that potential energy is it's dipping down. All right, and so let me show you that. Let me force these closer together. So we get to a point where we have no potential energy, they're just staying there. But once they get to a certain distance from each other, our potential energy dips down. And so what is happening there? This is when a bond is formed. When a bond is formed, you actually have your potential energy going to a lower energy state. Things like to go at lower energy states. That is more natural. And so since we're going to a lower energy state, when bonds are formed, something has to happen to that energy. So the energy is released to the surroundings. And so what you need to know from here is that when bonds are formed, energy is released to the surroundings. We see this and we know this because of that potential energy dipping down. You're going to a lower energy state when bonds are formed. So this right here is where my bonds are formed. Now, let's talk about what would happen if I were to put these guys closer together. Notice how they would repel from each other. That's because the two nuclei, when they come in too close of a proximity, those nuclei will repel one another and you spike up your potential energy there. So we don't want very high potential energy. We don't want a zero potential energy. We want a low enough potential energy state to create our bond. So what do I need to get out of this? You have to realize that when bonds are formed, it releases energy. So when bonds are formed, it releases energy. So if that's the case, what do you think happens if I break bonds? Think about breaking something, like breaking a couple of sticks together or something like that. Breaking some sticks up for some firewood. If I want to break something, I have to put in energy to do that. So the same idea is the case here. If I want to break bonds, I want to put in energy or absorb energy in order to do that. So why is this important? Well, this is important because when we're looking at our reactions, where we have reactants going to our products, we have to understand what is happening on each side of the reaction. For the reactants, what we're doing is we are breaking bonds in this case. So reactants, what we do is we break bonds. And by breaking those bonds, we have to put in energy or absorb energy to do that, okay? When we are forming our products, we are breaking these apart and forming new bonds. That's what's happening on the product side. So when we are producing our products, we are forming bonds. And when we form bonds, that is releasing energy in the process. So we talked about what this whole unit is about. It's about thermochemistry. It's about a transfer of energy. And that's what's happening when we have these reactions. You have your reactants that are breaking bonds, so they're having to absorb energy to do that. And then they are forming new products. So they are forming bonds, and that in turn is releasing energy. Now, whether or not your overall reaction, so we're talking about this overall reaction totally, whether or not this total reaction releases energy or absorbs energy, it depends on which side is greater. For instance, if I have to put a whole lot of energy in and I'm not getting much energy out of it, then that means that the system overall has absorbed more energy than released. So it's absorbed more energy, and we call that an endothermic reaction. So we have a term here, endothermic reaction. If I have more energy absorbed than my energy released, that is endothermic, and we give it a positive delta H quantity, okay? If I have formed more bonds, releasing more energy than I've had to put in, then we call that an exothermic process for that entire reaction process. And we give it a certain sign convention, and that is a negative delta H quantity. So endothermic, what does that mean? Overall, for the reaction, I have absorbed energy. Exothermic, what does that mean? For the entire reaction, looking everything as a whole, we have released energy. And where are we absorbing and releasing this energy? We are releasing it away from the reaction out to the surroundings. And so this is a very important concept for you guys to know. So this kind of gives you the main idea of what this unit is going to be about.